to the Friday Happy Math Hour. In this session, we're going to be talking about properties of triangles, volume, and surface area. So we actually started talking a little bit of geometry, finding the perimeter, finding areas last week, and this is a continuation towards the end of chapter 7. So the first topic that we talked about is similar objects. And similar objects, these are objects that have the same shape, but not necessarily the same size. So they have to kind of like match almost everything, but the sizes might be different. So examples would be, as you could see on the left, we have a couple of triangles. If you notice, they're kind of like slanted on the same direction. The sizes are different, but there's a similarity between them, which is why we call them similar triangles. Another example would be like cylinders, and I'm pretty sure there's lots of examples like these. Like maybe one of the kitchen tissue papers, and maybe like a roll of toilet paper. So those would be like similar. Or boxes. So similarity of objects may happen in two dimensions, like 2D things that are on a plane, or also like 3D objects. Like we could see the boxes; they also share the same similarities. Like they have the same construction, but it's just in a smaller size. In this section, we're gonna focus specifically on triangles. There's a lot of properties of triangles. Triangles are one of the centers of mathematics. They're like mathematics is centered around triangles so much because there's so many things. Even like in architecture, in construction, triangles are one of the most stable structures. So a lot of bridges are constructed using triangles because they properly distribute the weight. So in this section, the similarity of when triangles are similar, they have specific properties. And the first one is that the ratio of corresponding sides are equal. And so, for example, I think I actually have examples for this. In these two examples, where we see the triangle ABC, and then we have the triangle DEF, the larger one. The word ratio usually means fraction. So every time, I mean, simply put, mathematically, a ratio is a fraction. Let me say it that way. I like to translate everything in mathematical terms. Like, what does this mean mathematically? And the word ratio means fraction. Maybe someone like a scientist or an engineer will probably say a ratio is how two things change, like comparing two things. And this is exactly, it matches both definitions perfectly. So we see a fraction, and the two things that we're comparing is the base of the smaller triangle AB, which is equal to 2, so I substituted, divided over the base of the larger triangle, which is 6. And if you divide 2 by 6, you get, and you simplify, well, not really divide it, but if you simplify the fraction, you get 1/3. So when we talk about the ratio, we're talking about this fraction and its value. So AB over DE equals 1/3. And what the property says is that these triangles, the ratio of corresponding sides are equal. Notice that I selected the base on the smaller one and then selected the base on the larger one. So if I were to switch now a different side, on the smaller one, if I select BC, which we could say this is the right side of the triangle, and the corresponding one on the larger one would be EF, which is the right side of the larger triangle. And I substitute their values in the fraction, it gives me 1/3 as well. So this is what the property says. If you have similar triangles and you create the ratios of corresponding sides, you're gonna get the same number. So those ratios, those fractions are equal. So AB over DE is equal to BC over EF. And obviously, since the triangle has three sides, we could do one more. So the last side on the smaller one, I can take AC, and then on the larger one, I can take the F. Oh, something happened with my pen, which is not not writing anymore. But the idea is these sides AC over DF. Notice there's things to remember. Geometry is actually one of the, I find that beautiful. One of the beautiful things about geometry is that it's very organized, very structured. So all of these fractions, I started by selecting the smaller side and then the larger side. And so all of these fractions that you're creating, you're supposed to create them in that way. You always start on the smaller one and then you go. If you can switch it, but if you switch it when you do the divisions, you would start with like DE, which is the base of the larger one, divided by AB, or EF and then divided by BC. And notice that if you flip all of these fractions, you also get the same value, which is 3 over 1, 3 over 1, 3 over 1. They're all equal to 3. So you could switch. You could decide where you start, but once you start either on the smaller one, then you always need to have the values of the smaller one. All of those values, all of those sides, they need to be on top of the fraction AB, BC, and AC, which is the sides. And then below, you put all of the sides. You could switch it around, but just keep that keep that order. Okay, so that's the first property. We'll also have another property. This is actually the defining property of similar triangles, which is the measure of the corresponding angles is equal. And so on this slide, I actually have pointed out the corresponding angles. So if you look at the way, kind of like the orientation of the triangles, it's like they have this side on the right, and then each one has a side on the right. And then we have the angle. Usually when we talk about angles, it's best to leave the vertex in the middle. So if I want to talk about the red one, I would go like CAB. That has to be equal to FDE. Well, actually, since we have different letters, I could have just said angle A is equal to angle D. That would have been easier, huh? Angle A is equal. So the measurement, whatever, if this is 40 degrees, then the other one has to be exactly 40 degrees. And so if I now pick, let's say, C on the smaller triangle, which is in green, the corresponding one on the larger one would be F, because it's at the same location. It's at the corresponding location, like top angle matches top angle, bottom right angle matches with bottom right angle, left angle, bottom angle matches with left bottom angle. So those angles need to have exactly the same measurement. That's actually how we prove that two triangles are similar. By first, we check that all of the angles are that the corresponding angles are equal, which we can just say when we say all of the angles are equal, I mean like angle A corresponds to angle D, angle B corresponds to angle E, and angle C corresponds to angle F. Okay, one more property. So this one is actually a consequence from the top one. So we're putting it as a different one, but it pretty much is the same. So if you do the ratio of the corresponding heights, then it's equal to the ratio of the corresponding sides. So we saw before that every time that I divide AB over DE, if I divide the I got 1/3. So similarly, if I draw a height, it's going to be equal to the height on the larger one. However, when you do the heights, remember that to draw a height, a height is defined as a perpendicular line. If I want to know the height that falls on AB, then I go to the opposite vertex and then I draw a line from that vertex falling perpendicular onto the side AB. Often this height would be outside of the triangle. In fact, I would say for the most part, the height is usually inside the triangle, but in this, you can see it's outside. Just like also for the top triangle, the height lands outside. Let's do an actual example. So let's see how we can use these similar triangles to solve geometry questions, math questions. So the first example says triangles ABC and DEF are similar. Find FG, the height of triangle DEF. I like to point out how even the way the book writes the orientation of the triangles is very, let me see if I can write again. There, I can actually write. So triangle ABC, I like how the orientation is always maintained. So if you start on vertex A, you will go A, B, and then C. And so to name the other triangle, you would do in the same direction. Now, this may seem like, well, like, what's the point of doing that? If I give you 3 points, there's only one triangle that is determined by those 3 points, and that is true. But you'll see there's a payoff when you have similar triangles. It helps you create those ratios. That's what we're gonna use. That the ratios are equal. So these two triangles are similar. We can see the shapes. It may not be clear, but on the smaller one, we actually know 10 represents this side, and then on the larger one, DF represents that side. 15 is DF. And then they're telling us that the height on the smaller one, that's what there's a line pointing here, is 7. So we want to know the height of the larger one. So in this question, they are telling us that the triangles are similar, so we don't need to prove it. And if we look at them, they have the same shape. So we can move on. Because the triangles are similar, then if I divide the sides, if I divide AC over DF, which over AC over, what did I do? Over HC. I think I changed it up here. I apologize. So I didn't want to do that, and then now I realized I did it. Because initially I should have done AC divided by DF. And then this is equal to, now I could divide the heights. That would give, remember that the heights have the same ratio. So if I divide the height on the smaller one, CH, this would be equal, or HC, would be equal to the larger one, which is FG. And so I could use these fractions to solve and find the larger value. Because I know all of the other values. I know AC, I know CH, so I know this, and I know DF, so I can find what is the height FG that they're asking me. Now, the way that I wrote it here is actually not incorrect, but it might be confusing. Let me tell you just quickly how you can get from these to that one. So if you have AC is equal to DF over AC over DF equals to CH, you can actually move this one dividing, and you can pass this one multiplying, and it gives you this one. So it's actually equivalent. It's equivalent to the previous one. So dividing AC by its own height would give you the same ratio as dividing DF by its own height. And so what I'm going to do now is substitute, like I mentioned. I know the value of AC is 10. I know the value of DF is, where is DF? Here is 15. I know the value of HC, which is 7. So if I substitute these three values, I get this fraction. And you could solve this by cross multiplying. This is a property of equivalent fractions. When you have equivalent fractions, if you cross multiply, it gives you the same value. So if you multiply 10 times GF, this is the same as 15 times 7. And in a similar way, if you multiply 7, well, 10 times GF is going to be equal to 15 times 7. Now, from here, since I want to solve for GF, we could move the 10 dividing, and you get the following. You get that GF is equal to 15 times 7 divided by 10, which is 10.5. And so that is the answer. The height is actually 10.5. Notice that I wrote it as GF, and then initially they gave it as FG. That part, I probably should have kept it the same way they did it, but it doesn't change because it is a distance. So it is the same distance from F to G as it is from G to F. Okay, so that is how do you find the height using similar triangles. Let's do another example. In the next example, I have this figure, and it says that angle A and angle D are right angles. And I also have the AB is 10, so maybe I should put that information. So angle A is this, and angle D, and I'm putting a little square, and that square means that they're 90. So I don't even need to write 90. When I put that, I create a little square, which means it's a right angle. AB equals 10, so I know this length is 10, and CD is 4, which is over here. And DO is 3, which is from here to here. And I want to find what is the area of the triangle AO, and B. So this larger triangle. The strategy to find this triangle, notice that I can use as the base of the triangle any of these sides, AO or AB. If I use AB as the base, then the height would be this. The height would be AO because it's perpendicular. It falls perpendicular from this vertex all the way to this side. So this would be the height. And I'm emphasizing on that because the area of a triangle is base times height divided by 2. So I can use 10 as the base, so that would be 10. And the only thing that I need to find in order to finish this question is what is the height here? I could call it H. What is the size? What is the length of this side AO? Well, the strategy, I wish now I could delete all of this. Let me see if I can. Nope. So the strategy for this is that the way this is created, where this is an angle of 90 degrees and this is an angle of 90 degrees. And then, and these lines are kind of like crossing each other. That forces the top triangle being similar to the smaller one. So if we notice this side is actually opposite to this one, or vertical angle. And so they have the same measurement. And so keep in mind, this one has already an angle of 90 degrees. The smaller triangle has an angle of 90 degrees. Then this angle on the larger one is larger to the angle on the smaller one. Then the third angle has to also be equal. Now, the reason for that is because the sum has to be 180. So if two angles already are equal, then the third one has to be equal as well. So to check that two triangles are similar, all you need to do is prove that two angles are equal. So I'm going to do that because I'm going to use the property of similar triangles so that I can find, you know how it's going to work, because since I know the base on the smaller and the base on the larger one, and I know the height on the smaller one, then I could set up a fraction to find the height on the larger one. So that's my strategy. And once I know the height, I can find the area. So my goal is to prove that triangle A, O, and B is similar to triangle D, O, and C. Now, I mentioned before how the orientation is actually important. And so the idea is that to create this orientation, you would kind of like cut off the two triangles. And so this one, the larger one, triangle AOB, you actually need to rotate it into this direction so that it matches, so that they both have the angle of 90. And remember that these angle match, huh? So if I were to, with scissors, cut it out and then rotate it, it would look like this. So my angle of 90 degrees, I will rotate it until it lands there. So that's actually A. Notice how B would go all the way here. So B would be here and O would be on the top. And there, when I have them on the same orientation, if on the larger one, if I start with A and then I go to the top, O and B, then I need to match the same thing on the smaller one. So I will go with D, O, and then C. Now, once you have that, since the triangles are similar, we already established that they're similar because they have two angles that are equal. Then, those are the two angles that are equal. Then we have these three fractions that are equal. And without looking at the triangle, then you can just look at these letters. So if you divide AO, the first two, on the smaller one, on the bigger one, which is this, then you divide DO, which is the first two letters. So AO over DO. It's like this side corresponds to this one. And then I could do the same thing with the last two letters. OB corresponds to OC. And last, I could select the letters that are kind of like at first and at the end. AB corresponds to DC. So if you order the triangles, if you put the same orientation of the letters, matching angles, then you can just create the fractions in this way. This is one of the possible ways where a student can get this wrong, can get the answer wrong at the end, is if you don't set up the fractions correctly, which is why I'm kind of emphasizing a lot on it. And it is fun, it is very geometric, like I said. It uses a lot of imagination, like cut the triangle and then rotate it so that it matches, so that it's sitting in the same orientation that the smaller one is. All right. So now that I have those fractions, the ones that I want to emphasize is the ones that I know. So notice that we know AB. So out of those three fractions, I'm going to use, not always, in fact, whenever we have three fractions like this, for the most part, we only use two at a time. So the two that I want to use is the first one, AO over DO, equals AB over DC. Those are the two that I want. All three are equal, but I don't need the middle one for now. Because if you substitute those are the values that I know. AO is actually what I'm looking for, is the height. So I'm going to call it H. AB was given, that is 10. So I substituted AB with 10. And all of the other numbers, DO is 3, DC is 4, or CD is 4. So you end up getting this setup. And we can solve it, like I mentioned before, cross multiply. So this is going to be, or multiplication in diagonal if it's easier. Because sometimes when I say cross multiplication, people usually think across and they want to multiply the tops or the bottoms. So multiplicate cross usually is kind of like creating an X. So H times 4, which is 4 times H, and 3 times 10. And since this, I want to solve for H to cancel the 4, I divide by 4 on both sides. And I get 10 times 3 divided by 4, which is 30 divided by 4, and simplifies as 15 over 2. Now, if you want, you could put it as a decimal, but it's not necessary. To finish the question, I can write it down as. So remember my formula, since it's asking me for the area of the triangle, the larger one, it was base times height divided by 2. So I'm using the base as AB, which is 10. I already found the height by using the similar triangles, which is 15 over 2. And all of this divided by 2. Well, if you divide 10 times 15 over 2, you get 75. And when you divide that by 2, again, you could leave it as a fraction. On WebAssign, you can write this in this way using the diagonal. Or simply, if you want to write, because if you put this in a calculator, it only gives you one decimal, a terminating decimal, then you can input the answer either as a fraction or as a decimal. And that is the 37.5. And the units are centimeters squared. A couple of things to notice is that we saw at some point, and this is often very used in geometry, that the 3 dots means therefore. So it's like from the previous statement, since the triangles are similar, therefore we can use this formula. And then often these arrows, it's just like, what is the next step? So from here you go to that step, from here you go to that step. Last, on the question, they mentioned the area of the triangle, and you can represent the area of an object, of a shape, of a polygon by writing down their letters. So even though I didn't put the triangle, just by putting AOB is the area of that polygon. And since AOB encloses a triangle, this is how you will write down the area of the triangle AOB. Okay, so let's do another example. This is an application. This is a typical question that I put my students on the question because one of the goals is that we want to apply these in practical problems. And one of the ways that similar triangles are very popular to use is to find the height of a building. So if you have, you can use the shade of the shade created from the sun, the shadow created from the sun. So in this question, we have the given triangles are similar triangles. Use this fact to solve the exercise. Find the height of the building when x equals 1 meter and y equals 2 meters and d equals 2. So the typical question is that this is the ground level and we see the building in there and we want to find the height of the building. And maybe the sun is up here and somebody goes and looks at the shadow and you could measure the shadow. And we know in this question, the shadow is represented with the letter D, is the length from the base of the building all the way till the end of the shadow, and that is 2 meters. And the way that they usually use this, you can use this application, like if you're out in the street, you can measure the height of a person. So you could think this is a person that is standing there. And you, again, you put it in the same orientation, facing the same way that the building is facing, and then you measure the shadow. And most of the time, people would know their height, so that's why the height of the person. And then you can measure the shadow that the sun makes on the ground. Notice that we have those two measurements. X is actually 1 meter and Y is 2 meters. Well, with this information, we can actually find the height, and you could see it there. The goal in these questions is to find similar triangles, and the shadow makes the triangle. So we have the base, the height of the building, and then this diagonal or hypotenuse. And in a similar way, here in the smaller one, we have a base, the height, and then the shadow, the diagonal that creates the triangle. So these triangles are actually similar. And since they're similar, then the ratios of the corresponding sides are equal. So that means if you divide the height on the larger one, that's equivalent to the height on the small, well, height of the larger one over the height on the smaller one. That equals the base on the larger one divided by the base on the smaller one, which is this part of the formula. Next, substitute all of the numbers that we know. So we know that D equals T, 2, Y equals 2, and X equals 1. So after you substitute your variables, you multiply. I'm gonna continue saying it because that's how I called it all the time. Cross multiplication, which is like this X. Maybe I should change it to X multiplication or diagonal multiplications. It'll be h times 1 equals 2 times 2, and then solve for h. If you prefer, you want to cancel that 1, you could move the 1 dividing because it's multiplying. So to eliminate it, you divide on both sides of the equation, and you end up getting that h equals 2 times 2 over 1, which is 4 over 1, which is 4. So the height of the building is 4 meters. So this is a typical application of similar triangles to identify the height of a building using, or height of anything, not just the height of a pole, using shadows. Let's go on to the next topic. One of the important properties of triangles is, of course, the Pythagorean or Pythagoras theorem. And most students know this one. This is a very popular. Almost everybody has heard once in their life Pythagoras theorem, which is if A and B are the lengths of the legs of a right triangle, and C is the length of the hypotenuse, then A squared plus B squared equals C squared. And this is a typical picture. And the way this, obviously the square, usually the square represents the area of a triangle of length, of a square of length A. So if you look at the base, and this is what we're calling the leg. So this would be one of the legs, and the height would be another leg. Keep in mind that the legs are interchangeable. The only one that always is fixed and set is the hypotenuse. I always like to remind my students, because sometimes this gets confused, that the hypotenuse is the opposite side. So if you identify the angle of 90 degrees, it's across of it, it's opposite to that. So the only one that doesn't change is C. I could change the letters like this. I could call it B and I could call this A. But very important that C always represents the hypotenuse. Let's use it to solve a question. The question says the hypotenuse of a right triangle measures 6 meters and one leg measures 2 meters. Find the measure of the other leg, round to the nearest hundredth of a meter. The answer, I created a triangle. I was not given a triangle, but in geometry, we always recommend create a picture that has the information of the problem, that represents the problem. So this is my right triangle. I labeled it ABC. And then the right angle falls here on the B angle. And as mentioned before, they tell us that one of the legs measures 2 meters. It doesn't matter which one you choose, this one or the other one. You still get the same answer. So I chose this to be 4. I chose this to be X. The hypotenuse, that now, this is always the longest side, the one that is opposite to the angle of 90 degrees. So that has to be 6. That cannot be changed or modified. Also, when you do the formula, as I mentioned, you could call this A, or you could decide the bottom one to be A. That does not change. The only thing that is very important is that C is always the hypotenuse. So now that I call this A, so A equals 2. So technically, I want to find B. What's the value of B? So my formula is A squared plus B squared equals C squared. That's the Pythagoras theorem. And so A squared is going to be, did I do this incorrectly? No, because I mean, on the picture is incorrectly. Now I realize this is 2, because the leg measures 2. And then when you square it, you get the 4. So 2 squared is actually 4. And then B is, I call it X over here. That's what we don't know. We want to find that value. We know that the diagonal or the hypotenuse is 6. So 2 squared is 4 plus B squared, which I don't know. So I'm going to leave it as a variable. 6 squared is 36. And then solve for B. So move the 4 on the other side by subtracting 4. It cancels and you get B squared equals 36 minus 4, which is 32. And finally, the last step, to cancel the exponent 2, you got to apply the inverse of the power. And the inverse of the power is the root, the square root. So find the square root of 32. And in this question, they do ask us to round the answer to the 100th meter. So I went and put this in a calculator, and 100th usually mean, not usually, always it means um, round to 2 decimals, and rounded to 2 decimals, the answer is 5.66. Okay, so let's do another one. Now, this is the last part of my talk. Heading towards the last part, I am going to talk about volumes, and I also want to talk about surface area. So the volume is a measure of a space that a solid has. And so I put this picture so that we could compare the difference. The area is for something that is 2D, a two-dimensional shape. So it doesn't have a thickness. If you could think of this like the mat on a table, and so the area tells us like how much surface the mat or the shape covers, like what is inside. What is that? When we talk about a space, it's like you're feeling it. It's in a three-dimensional object, like a box, and you see the box. And so how much space can you fill in there? That is the volume. The units of area are usually square. The units of volume, they're usually cube. So not to be confused, areas and volumes. These are the typical formulas to find volumes. I usually call this shape the box, the rectangular box, but the proper name, it's a prism. So a prism usually refers to these boxes. So the area of a box or a prism would be length times width times height. So this is, I don't have like a multiplication sign, but remember that in algebra, if you have letters together, it implies multiplication. So this is L times W times H. For the cube is like the special case when all of the sides are equal. So it's like a box, really nice. All of the sides are equal. The length of all the sides are equal. And so if you substitute, it will be like S times S times S, which reduces to S to the cube power. In a similar way, a sphere has a special formula to find the volume or a space inside of it. The formula is 4/3 times pi times radius to the power 3. A cylinder is like a roll, tissue roll, a roll of tissue paper. And to find the space that it has inside, actually, this is very intuitive. If you find the area of the base and then you just multiply it by the height, since on the base you have a circle, it would be pi times radius squared and then multiply by the height. A cone is actually very similar to a cylinder, but it has the added 1/3. Now, if you would want to know where do these formulas come from, for example, why a cone is 1/3 of a cylinder, or why the sphere has these 4/3, these can be found when you study probably calculus 2 and calculus 3. You can use integrals to find these formulas. So if if you're curious to know where these formulas come from, a good idea would be to take an advanced course in math so that you can understand why these formulas are the way that they are. Pyramids, we have different shapes of pyramids. Very often a pyramid has a triangular base, but depending on how the base is, the formula may change. So the formula that I included in this table is a square pyramid, which has a square on the base. So the volume of the pyramid would be 1/3 of S squared times H. All right. So now I'm gonna move on to do a question using that table. Example, the radius of the base of a cone is 8 centimeters. So this is a cone. First of all, identify where you're finding. What shape we're interested in. The height of the cone is 12 centimeters. Find the volume of the cone. And this is what we want to find, the volume. So we can go into the previous page and look at the formula. I already have it. So this is the cone. We're given that the radius of the base, so the cone is lying on the circle, huh? That's the way that it would be stable. And the radius of that is 8. So this picture is actually, it was supposed to be an 8. There, the radius is 8, the height is 12. Wow, I wonder why my numbers are so different. The height is 12. Okay, so then let's use the formula. Radius is 8. Oh, this is actually, it changed it to A, but then on the bottom, no, I still had it wrong, huh? Seems like it switched them out. I'm not going to change the picture, but the radius is 8 and the height, so H is 2. This is my formula. Substitute, so to find the value, I substitute those values. So it's 1/3 times pi times radius squared, which is 8 squared, and then times height, which is 12. And follow PEMDAS, do the exponent. A squared is 8 times 8, which is 64. Then multiply 64 times 12, that's 768. And since we're asked to round to the nearest hundredth, we also want to put all of this in the calculator, which would be like 1/3 times pi times 768. Last time we talked about what an exact answer is, and an exact answer usually does not have decimals. So if you multiply 1/3 times 768, you get 256 times pi. So I didn't multiply by pi. This would be the exact answer. So if it asked me to enter the exact answer, I would enter that. But because it is asking me to round to the nearest hundredth, so I even multiply that by pi, and this is approximately 804.25. And I did not put the units, but it's good to keep track of the units just so that you know that it's kind of like everything matches. Like I found the volume because my units are cubic centimeters. All right, let's do another example. So the next part, and this is what I mentioned that I also wanted to talk about, the surface area. The surface area, for whatever reason, is always one of the difficult ones for students. This refers to the area of the total surface, so everything that surrounds the solid. So if you have a cube, the easiest way to explain the surface area is that you think of the solid, the 3D picture like a cube, and then you unfold it. You look at all of the faces. So what is the area on the face? Not the space inside, but on it, on the surface of it. And so usually something that we learn in previous math classes is that you could create this shape by using nets. We call these patterns nets. So if you fold it and fold it on the lines, this would create a cube. And the net is very useful because you can see all of the sides. So for example, a cube that has 6 sides, and you could see them here, 1, 2, 3, 4, 5, 6. So you could fold it. Maybe this could be your base, and this would be the left side, the right side, and this would be the top once you fold it. So it is 4 sides, the base, and the top. Well, if you want to, the area of each one of these squares would be s squared, because in a cube, all of the lengths are equal. So the area of this square is s times s, which is s squared. And because there's 6 of them for 6 sides, then the surface area would be a total of 6 times s squared. Well, that was kind of like the easy one, so I went over the detail of it. If you have a cylinder and you cut it, let's say that you cut the cylinder with scissors right here, what you get is these extends on both directions, and you, let's say that the cut happened right here. So if you were to, you end up getting a rectangle. That's the, so the surface area of the body of the cylinder is a rectangle. And then if this is a closed cylinder where you have a top and you have a bottom, then the area on top and the area on bottom are two circles. So to find the surface area, I gotta find the area of the rectangle and the area of the two circles. So the area of a circle is pi times radius squared. And if you notice on the formula, I have that multiplied by 2 because it's two circles. Now, the deal with the cylinder is that the area, to find the length that you create, basically this length, when you fold this rectangle into the cylinder, it becomes the circumference. It becomes a circle. And so the circumference of a circle is 2 pi times radius. So that multiply that by the height. And so this is the total area for the cylinder. Now, I'm not going to explain the last two, but you could kind of like analyze them in a similar way. So if you have a square pyramid, um, to find the surface area, it would be s squared, which is the base, and then plus 2 times s times L, where L represents the slant height. So it's not the height of the pyramid, but the height of one of those triangles. So this would be like on, if you do the height on that triangle, on a face of the pyramid. Last, the cone. If you unfold the cone, it looks like a circular sector, which is this top piece. It looks kind of like a fan. And then the base of it is a circle. So the surface area is pi times radius squared plus pi times radius times L, where L is the slant height. It's the length on the side. Okay. So I'm gonna do just one question. It says, example 2, the diameter of the base of a cylinder is 6 feet and the height is 8 feet. Find the surface area of the cylinder. Round to the nearest hundredth of a square foot. Keep in mind that in this question, they gave us the diameter of the cylinder. And so that would be from one side of the circle to the other side. So this length is what it is, 6. When I look at my formula, the formula for the surface area of a cylinder is, again, 2 pi radius squared plus, remember, this is taking into account that the cylinder is closed on the, kind of like a can of like canned veggies, where it would be closed on top and closed on bottom. Very important to read on the instructions whether the cylinder is open, because if it's not open, then you probably only want to include one of them. So instead of having 2, just 1 would be fine. But notice that here I need the radius on these two pieces, and I'm given that the diameter is 6, but the diameter is twice the radius. So if I divide 6 by 2, it gives me that the radius is 3. So from the center to one of the sides is 3. And then the height is 8. So the rest would be just substituting to that formula. So substitute 2 pi times 3 squared, which is the radius, plus 2 pi times 3 times 8. Remember, do PEMDAS first, exponents first. 3 squared is 9, 3 times 8 is going to be 24. And then 2 times 9, you could actually multiply the 2 and the 9 and leave the pi at the end. So this is 18 pi. Similarly, 2 and 24, that would be 48, and leave the pi on the right. And these are similar terms, so you can actually add them. So the exact answer, the exact area is 66 pi. But since we are told to round these to the nearest hundredth, then we do one more step, multiply the 66 by pi. And this is actually 207.35 square feet. Now, even though I'm using a solid, which is a three-dimensional object, since I'm finding area, I'm finding the surface area, then the units should be in square units. Okay, so today that was the end of my presentation. I hope you all had a good review of geometry and properties of triangles, and I'm going to pass the host to.
Thank you so much. Thank you
Yes,
so
thank
much,
you,
Mr. Tinto. This is Sandra, Mr. Tinto. Thank you so
Miss
much for
Sandra.
presenting. Yes. Thank you so much for presenting today, and thank you all for coming and being such a wonderful audience. And we definitely hope to see you again soon. So please join us next week for Math 1332. We'll be covering Euler circuits, weighted graphs, the counting principle, permutations, combinations, probability, and odds. And for Math 2412, conics, parabolas, ellipses, hyperbolas, and parametric equations. So please join us next week, and you all have a great and amazing weekend. Thank you. Bye.
Thank you.
Bye-bye.
Bye,
Bye.
everybody. Thank you for listening.
Bye.
Thank you, Mr. Tintos. Have a good weekend. We'll see you next week.
Have a nice weekend, everyone.
Bye, everybody.
Have a
Thank you,
nice
Evelyn,
weekend.
Sandra. Good job. Thank you, Tim. We'll see you guys later.
Happy Friday.
Happy Friday. Lynn, the
That's
session is
true.
over.
Happy Friday.
We'll see you next week, Lynn. Bye-bye.